Hey, this is a review of plate tectonics. The waterfall in the background actually has a nice thrust fault associated with colliding plates with it. So let's put this here. If the computer will pay attention and respond. There we go. What powers plate tectonics? You have the convection in the mantle, circulation of hot rock, rising up in one area underneath our mid-ocean ridge here, and sinking down in other areas. This is actually rock again, not liquid, but it is hot enough to be squishy. And so slowly the hot rock will rise, pushing its way up, and the cold sink down. And the plate is riding along on this. We also have the push out from the mid-ocean ridge, being a ridge sticking up. Gravity's pulling down, the rising stuff pushing all that together. And then at the far end, we have the sinking slab, a trench, and that pulls the rest behind it. And we also get suction as pieces break off the end of the plate and sink down. As it sinks through other rock, it sets up suction, kind of like the way trying to pull your foot out of the mud produces suction. Right at the mid-ocean ridge, hot rock is moving up from below. Hot, less dense, expands, so it's going to make a ridge being higher. Less dense sits higher. This is different from hotspots. Hotspots are a relatively small column of hot rock. This is a very large-scale loop creating a long line of the mid-ocean ridge, not just one spot. Move my picture up so it's not in the way. Plates are moving apart. They are diverging. And so as two sides move apart, what's in between tends to slide down, forming a rift valley. As they move apart, this gives us lots of earthquakes, but typically fairly small and quite shallow in the earth. As the plates are pulling, we get cracks, and these allow water from above and magma from below to fill in. And of course, the water in there gets quite hot, and you get the black smokers, the deep sea hot springs, all those sorts of things. Relatively calm volcanism. The magma or lava, if it's at the surface in the cracks, formed by the melting of that hot rock, cools down, forming our darker, denser rocks like basalt. And as it cools, eventually reaches the temperature where the magnetic field will be frozen in place, and the magnetic bits in the rock will be stuck, generally lined up with the Earth's magnetic field like tiny compass needles. As new rock continues to form behind it, older bits will gradually be moving out to the side. They're also getting older and colder and denser and sink deeper down. So from being part of a ridge, they eventually become part of the abyssal plain. we start to get sediment, sand and mud piling up, skeletons, all that sort of thing. And so the further we are out from mid-ocean ridge, the older the rock, and the more layers of sediment we get on top of it. If they're islands, weather, waves, all that tend to wear them down until from a taller, typically volcanic island, we get an old flat island. But again, the plate underneath it is cooling and sinking as it moves on. So eventually that island will end up as a flat top undersea mountain, a guyot. Magnetism, well, that's still stuck, so it's not going to change. So the rock, the cursor reappears. Rock here, magnetic bits were lined up with the Earth's magnetic field when it formed, and it stays that way as it keeps moving out. But eventually the Earth's magnetic field flips, and now rock behind it is getting magnetism going the other way. Eventually, the old, cold, dense ocean lithosphere runs into another plate and can get shoved down at a trench. Lots of sediment piled up. This is relatively old. The mid-ocean ridge is way off to the left somewhere. As the plate goes under, some of that sediment gets scraped off. Of course, it gets a little more messy to scrape if it's a whole mountain attached to the plate, but it does eventually get broken down, scraped off. Of course, you're going to have some earthquakes in the process. With this, we have, get me out of the way of some of the words here. Earthquakes, some of them small, but they can be very, very big. The very biggest earthquakes that we've ever measured have been associated with trenches. And again, because one plate is going down underneath another, yeah, virtual background makes things interesting here. Some of those earthquakes can be very deep down in the earth. The very deep earthquakes are only associated with trenches. The link here goes to a video of the pattern of earthquakes from, I think the smallest they've gotten there is about 4.5, which if you're close to it and that earthquake is very shallow in the ground, that could be bad news for your china dishes. But usually a 4.5 is not enough to do any serious damage. And if you had a really flimsy house, it might fall down, but hopefully not. Goes all the way up to very big ones. 2011, you might remember that was the year with the huge earthquake hitting Japan. And if you watch the video, you will know when that one hits. The video does have sound with louder sound indicating bigger earthquakes. And you'll also notice there are aftershocks with the big one hitting Japan. Those will be quite conspicuous. It's a fun video to watch. It gives a lot of detail, particularly just kind of seeing the year accumulating in earthquakes. And I'll try opening it up for a bit here to give an idea. There it is. Okay, so you can see it's in Japanese and in English. It shows bigger circles and louder noise going with different sizes of earthquakes in terms of energy. It also shows you depth if you're looking at that. So here you see the basic pattern. Just to note, okay, this is things through January. The yellow line building up over here is showing the total number of earthquakes large enough for them to have counted to that point in the year. So you can see a little over 650 in 1 month. The yellow dots show where earthquakes have occurred that they're tracking. So you can already start to see a pattern. There are definitely more earthquakes in some places and other places that have distinctly fewer. By the time you get all the way through the year, it's quite easy to see a number of the plate boundaries because that's where earthquakes are concentrated. Now, if you look close, you may note a few quakes that are farther from plate boundaries, but even at this point, you can see distinctly edges of the Pacific. Like here's the Philippine plate with earthquakes around either side of it. Here's Australian plate plowing into Asia. Fewer earthquakes big enough to show up here, but we do see ones along the East Pacific Rise, the mid-ocean ridge for the Pacific. Also over here along the Atlantic, edge of the Caribbean plate, we've got some quakes there. Scrolling down here are the largest quakes, so it gives the magnitude and where it was, and over here is the depth and date. So let's get back to our PowerPoint again. And I'll let you watch it and see if you can tell when the big one hits in Japan. As our plate goes down in our convergent ocean-ocean boundary, it's getting hotter, we get melting, and we get volcanoes associated with that sinking plate. Compression, heating, eventually it may break off and sink further, but we get suction still associated with that, helping keep the plate on pulling on down. Besides our divergent, going apart boundaries, mid-ocean ridge typically, our convergent boundaries, whether it's ocean-ocean, ocean continent, either one of those give us a trench with lots of earthquakes going way deep in the ground and a volcanic chain. The difference is if it's ocean on both sides, that chain will be volcanic islands. If it's land on one side, ocean on the other, then we'll have a chain of volcanic mountains up on the land. Transfer boundaries, that's where you have one plate sliding past another plate. Usually geologic plates look a little different from those, although they are made from China, it looks like, which is made from clay. Our hotspots, useful markers of plate movement, though they're not directly related to the plate motion. We have the mantle plume, the column of hot rock, and especially as it rises, gets under lower pressure, we get some melting happening in there. It starts rather deep down the mantle. As it reaches the surface, we get a volcano forming over it. Now, sometimes we might not get lava actually at the surface, and instead we get a bulge. There's different possible ways it might show up at the surface. But our plates are moving. And so as the plate moves along, the old volcanoes move away, they erode, and new ones form over where the hot spot is relative to the plate now. So looking for older and older volcanoes, those will be further and further in the direction that the plate is moving. Again, difference between a hot spot and the mantle convection pattern. Mantle convection is a very large-scale pattern of circulation within the Earth's mantle. Hot rock is moving up all along the mid-ocean ridge, and then moves out sideways under the plate, cooling, and eventually sinking around the trenches. Hot spots are a mantle plume, pretty local, narrow column. They're under just one island or volcano group, like the Hawaiian hotspot, famous there. Galapagos hotspot, somewhere right around there's Samoa hotspot. I didn't draw that one in. A hotspot, since it starts out way down near the bottom of the mantle, doesn't know what the plate's doing up above. So any part of the plate can move across a hotspot. The Hawaiian hotspot's way out in the middle of the plate, not near a boundary. Galapagos hotspot is right next to the boundary here between the Cocos and Nazca plates, not too far from the edge with South American plate either. Iceland, that's a hotspot that's at the mid-ocean ridge. So hotspot can be anywhere relative to the plate. It's the ones out in the middle, like Hawaii, that really nicely give a good track of how the plate has moved. Galapagos, it's pretty messy. It's right around the plate boundary. Sometimes it's been to one, sometimes the other. Doesn't give you a very nice chain. Samoa is right near plate boundary too. Different types of valleys that we may see with the ocean. Trenches, these are the very deepest, the biggest. These are found at convergent boundaries that have an ocean plate, and could be another ocean plate, could be a continental land plate on the other side. The trench is there as a valley because the one ocean plate is being pushed down and bent under the other plate. So that gives us the valley there. The top is at the deepest point, and also the depth of the valley is extremely deep. Our rift valleys are at the divergent boundaries, where the two sides are pulling apart. As the sides pull apart, stuff in the middle tends to fall down into that gap along the middle of the mid-ocean ridge. On the ridge, so they're noticeably shallower, only usually 2 to 3 kilometers, so between about 1.5 to 2 miles there. Not as big as the trench for the depth. Our submarine canyons cut into the continental slopes. These are formed by erosion, not by plate motion. Although, of course, as plates move around, they do get cracks, and that can be an easier spot to erode. There potentially could be a distant connection, but the immediate cause of our submarine canyons, those come from erosion along the continental slope. So these are the shallowest in the ocean. The top may be only 100 to 200 meters down. Fancy high-tech scuba diving could potentially get you to there, whereas only very few submarines will get you as deep as the top of a trench, much less the bottom. They are deep canyons, big compared to any that we see up on land. And then our fracture zones. These cut into the sides of the mid-ocean ridge, but they're cutting across the direction of the ridge. And these are with the faults with the zigzags in the mid-ocean ridge. As we move out from the ridge, eventually we reach the point where both sides of the fault are going the same direction, but we've got a crack left from the formation in the zigzag. So those are in between, not nearly as deep down as the trench. They are on the sides of the ridge. So in relatively younger, warmer, less dense rock. But they can be decent sized valleys as well. Again, key importance of plate tectonics, besides just understanding how the world works and trying to avoid earthquakes and volcanoes, is that it provides an overall recycling of materials. What goes down, gets buried away in the earth, is not lost forever. It can be brought back up by plate tectonics. New rock is forming by material rising up from deep in the earth, cools, gradually pushed, pulled, carried out to the sides, end up as part of the plains, eventually down the trench, and mixed in to go through once more. As we saw, this is a key player in helping maintain balance of things such as carbon. A comparison, you can think about your fingernails. Plates have a spot where they're forming. For plates, it's the mid-ocean ridge. For you, it's at the base of the fingernail. And move on out. So you get the area, okay, middle of your finger would be the equivalent of the abyssal plain. And then finally, at the end, we have where the plate gets destroyed away, kind of equivalent to a trench there. Unfortunately, fingernails usually do not collide as they grow. Finger quakes might not feel so great. But you get the idea that if you were to hold your fingers together, eventually you'd have problems if you really sat there for a really long time. Same sort of thing is going on with the plates, except of course, nobody has to sit there holding them. The earth holds them up, so they have time to collide even though they're only moving about as fast as your fingernails are growing. So hopefully that's a helpful review of plate tectonics. Reminder of major factors there. And we can end things for now.